vascular tunics. So the fibrous tunic, the sclera is the dense fibrous connective tissue, the white of the eye, and the cornea that's transparent and lets light into the eyeball. The vascular tunic is where the blood vessels are. They have the ciliary body and the ciliary muscles that are attached to the lenses, and the attachment of the ciliary body to the lenses allows the lens to be pulled to a long position versus a stubby or a flattened or different arrangement, so that we can focus on different objects depending upon their distance. The vascular tunic provides blood vessels, the amount of light entering the eye based upon the pupil, and secrete and absorb aqueous humor and adjust the lens shape for focusing. The pupillary muscles are around the pupil. You have the dilator muscles and the constrictors. So the pupillary constrictor, the pupillary dilator, those are all going to control. In very, very bright light, your pupil is going to be very, very small. In low light, if you decrease light intensity from sympathetic stimulation, you'll get a very, very dilated pupil. In high light, you'll get a very, very constricted pupil. Okay, we talked enough about those. Let's look at the retina. There'll be questions on WebAssign. So when light flows and hits the neural tunic, you can see that there are ganglion cells, bipolar cells, and then rods and cones, and then the pigmented layer, and then the choroid. So light has to go through these various layers of the retina until it gets to the rods and cones, and that's where light will cause a chemical change and an electrical change in the rods and cones, and information is sent through these bipolar cells and ganglion cells. That information is carried to the visual cortex, and it's amazing what we can see. It's amazing, just amazing. Okay, so the retina is the innermost tunic of the eye. Information gets to the rods and cones, and it causes changes in the electrical conditions of the rods and cones, and they send a message. So that message is sent down the optic nerve, and the optic disc is where there are no rods and cones, so that's the blind spot. If you look at an ophthalmoscope view of the eyeball, you see the optic disc, the blind spot. The macula lutea and the fovea are another structure where there are lots and lots of cones. So this is the optic disc. That's where the blind spot is. You can see the eye has a very, very extensive blood supply, which is a very, very active tissue, and the fact that we are constantly using it to survive and prosper. Okay, there's two cavities of the eye. So we have, I just want you to know, this is the anterior chamber. This is the posterior cavity. This contains aqueous humor. This contains vitreous humor. And these fluids are in these various compartments to help maintain the shape and to prevent collapse of the eyeball. So they're all going to be important. This aqueous fluid here, this vitreous humor here, that's going to help prevent collapse and maintain the shape of the eyeball. Here's the ciliary processes. These processes, depending upon whether the muscles are contracted or not, that's going to change the shape of the lens so that we can focus on various objects, either far away or close. I'm having cataract surgery on May 3rd because my lenses are cloudy, and I gotta have artificial lenses put in here so I can see again. So that'll be a very, very important change for me. Okay. So the lens is suspended. Some transparent cells. Their job is to focus light. Accommodation is able to change the lens shape to focus on various objects at varying distances. Okay. So light goes through the cornea, goes through the pupil and so on, and the iris. It ends up at the retina. Cones are most abundant at the fovea and macula lutea. I said that before. Rods are dominant in the peripheral retina, and they respond to dim light. Cones are most abundant in the fovea and macula lutea, and cones respond most strongly to bright light and colors. So there's two types of photoreceptors. The rods are highly sensitive to non-color vision. These are less sensitive, so cones respond to bright light, color vision, and in the fovea, it's the site of the sharpest vision. So if we look at a diagram showing the rods and cones, so here's a cone, here's rods, and the light is going to come in, and the light is going to cause changes in chemicals that are going to lead to changes in the potential of the rods and cones, and that's going to generate action potentials or nerve impulses that end up in the visual cortex, in the occipital lobe of the brain, and that's going to allow us to process vision. Just think of the detail that we can see and distinguish. Just an amazing, amazing sensory structure of the eyes. Most animals have eyes. They all work in a similar fashion. So the chemicals in the rods and cones, the changes in the shape of these chemicals causes different ions to move in and out of the retina in the rods and cones. And when light stimulates this structure, the opsin, you can see that it changes the shape of the retinal, and that uses energy, and that change in the shape of the chemical is going to lead to the change in the movement of ions in and out of the cell, the sodium and potassium and so on. So what's the visual pathway? So here are your eyes. You have the optic nerve cranial nerve 2, where they cross at the optic chiasma, the optic tract, into the thalamic nucleus, projection fibers, and into the visual cortex. So there'll be question about the optic nerve, the optic chiasm, and that's the pathway from the eyes to the visual cortex, where the brain processes all that information, and it works pretty quickly and accurately. It's astounding. Okay, let's stop there. Go back, stop the recording. Okay.